the third of our four-part series on innovation, Steel Thoughts hears from Pedro Prendes, Head of Process Development, Global R&D, about the work being undertaken to develop breakthrough process innovations that deliver sustainability benefits and meet current and emerging environmental challenges.
Pedro, what's the scope of research, or rather the research challenge, when it comes to addressing the climate impact of steel? Because we're talking about a very wide selection of processes and steps. From an R&D perspective, what are you looking at when you're trying to address more broadly the environmental challenge?
Yeah, thank you for the question, because it's important to highlight that the steel is one of those difficult segments. When it comes to abate CO2, it's difficult. And the reason is that it's a very long production chain, that it starts in the mine. So we are working on the decarbonization of our mining products, of the production of iron ores, of the production of pellets, of the production of the raw materials that we will use in the blast furnace. Then we have the iron making itself, which is a major point of concern, because it's where we produce most of the CO2, especially in the blast furnace, but also in the sinter plant. And then everything produces CO2, and the production route is very large. We produce at the steel making, at the hot strip mill, and then we go into finishing. And everyone is always talking about the flagship projects, and how to decarbonize steel making, how to decarbonize the blast furnace, carbon capture, use of hydrogen, top gas recycling, and then we have breakthrough technologies, electrolysis of iron. But we need to make sure that we decarbonize the full route. This means that we look for solutions to decarbonize pelletizing plants, to find alternatives that are much more efficient and less energy consuming than pellets in our mining portfolio. And then really we are a very large company. We have a very large geographical presence. The heritage of several processes of mergers and acquisitions. We have a lot of technologies. We are the champions in blast furnaces. We are the company that owns a higher number of DRIs. We have a lot of experience in EAF, and we need to bring solutions from R&D to all of these situations and all of these assets. And at the same time, we want to go further. We want to be more bold. And we are working in breakthrough options like the electrolysis of iron, our project Volteron.
It's a broad challenge. Does that mean you have a very large organization, or does it mean you have to prioritize and pick the sort of the best options to tackle first?
Yeah, we have a lot of experience making R&D and making a successful R&D, and we are very applied R&D organization, meaning that we have a lot of interactions with our business, with our CTO teams, and we have very good steering tools in place, meaning that there is a strategy of the company. In this strategy of the company, it needs to be very clear what the company is expecting R&D to do. And we are having a very good split of responsibility. Our CTO colleagues are focusing in the short term in the available solutions, leading discussions with OEM. And R&D is always one or two steps ahead, trying to bring to reality some lower TRL technologies. We are in exploration mode. We are discussing what could be the solution in 10 years, in 15 years. But obviously, we are also supporting the application of the existing.
So, TRL being technology readiness level, where it's at in the sort of the journey from lab to application.
Yeah, when something is above 7, 7 is already a pilot industrial plant in operation, and 8 and 9 is when it becomes, let's say, industrial bread and butter. When it's easy, when it's well proven and very solid. R&D is working in lower TRL. We are identifying opportunities from TRL 2, TRL 3. We are using our lab and pilot facilities, exploring the TRL 5, 6. And then when we go into the first industrial pilots, we reach the TRL 7. This is, for example, where we want to arrive by the end of this year in our Volteron project. We want to be fully ready for industrialization, and we have made a great progress during the last years in this domain.
So we'll come back to Volteron in a second because that is a fascinating project. But just in terms of the prioritization and the investment in R&D, you talked about how integrated R&D is with the rest of the organization and sort of operationally. Does that mean the projects are driven by regulation and having to hit certain standards, or is there a sort of an economic driver to a lot of this as well? Because I'd like to think there's some crossover between doing things in a more environmentally friendly fashion, but also doing things in a more sort of economically profitable fashion.
Yeah, one cannot exist without the other. We need the economical motivation. We need to find solutions that make sense. One of our missions in R&D is to help to make our company sustainable. Meaning, sustainable, it means producing sustainable products. So we need to produce things that the people want to buy. We need to do it in a way which is compliant. We need to respect regulation, and we need to do that in a way which is economically feasible. If R&D develops technologies that are not economically viable, we have nothing. And very often we stop some research line because it's not feasible. It's technically is nice, technically is possible, but we need to keep our feet on the ground. I told you we are an R&D organization of a very strong industrial company, and we are very applied R&D, meaning that we know that our target is to support the business and to bring enough innovation and differentiation to ensure the long-term sustainability. But for us, the cost is always a basic target and is a paradigm. No matter the technology, if it does not work from the cost perspective, it's death.
Just explain for a layman like me the electrolysis process and how that works, because it's kind of fascinating that you can sort of put in water, iron, electricity, and it sort of or electricity and extract something really useful.
Well, yes, the electrolysis itself is a very old process, and it's existing since it's existing in nature, but it was discovered and developed 200 years ago. No? So it's not a new process. And there are some metals today that are produced with electrolysis on normal basis. It's like copper, like zinc, and it is something very simple. You put one electrons to circulate through a media. Water, it can be water with some salt. You need to conduct electricity, so you need these electrons to move, and these electrons go to iron oxide, and this iron oxide breaks and releases oxygen and metallic iron. So you need electrons, you need electricity, you need a media to conduct this electricity, and you need the iron oxide reachable by these electrons, and this is the electrolysis. And in any college, in any school, you can do an experiment. You can create a mixture of water, salt, you put some ions of some metal, and you can do some electrolysis. When doing that, you are also producing some hydrogen because you are also breaking some water, and you are releasing oxygen. And this is electrolysis. Why is not largely applied today for iron making? Okay, because until now the context was not good. We could not compete with a very efficient reactor like the blast furnace. We could not be feasible from the cost perspective, and also it's not easy. Also, the optimal solution we are developing has some technology handicaps that we are solving, that we have found through many years, and this is electrolysis.
From my curiosity, does the process produce useful amounts of hydrogen and oxygen? Would you be capturing that as a byproduct and selling it?
Well, yeah. Hopefully not, because what we need is to ensure that the electrons go for the reduction of the oxide. The production of hydrogen is a collateral
inefficient
damage,
process.
It's because if you have water, yes, it's a drop of efficiency. You can always think in recovering this hydrogen and the oxygen, but then you complexify the design and the machine. So the optimal is to find some working condition where we maximize the efficiency to a point where you don't need to recover this because this is minimal. Obviously, there is always emission of oxygen, that's for sure. But hydrogen is a signal of drop of efficiency, and it's better not to have it.
You mentioned Volteron there, which is a really interesting project. This is an electrolysis project, an alternative way of making making iron. Talk to me about that, because that's now at a sort of technology readiness level of 6, 7 around there today.
Yes, this is where we have brought it. We started to work on this before 2004. We started working in European funded project. We really appreciate the support when you have a very low TRL of the European Union to finance these activities, and we started with a project called UlcoWin. Then we were upscaling the technology. We saw promising figures of electricity consumption. We started to think this is possible, we could do it, and then we started to go up to upscale in TRL level. We built Cedarwind. It's the last European funded project we have been working, which we terminated in 23. And then we decided what is next. And next is to go into industrialization, but first to prove that it's feasible, to prove its financial viability. And for this, we launched a project with a partner, with John Cockerill. The project is called Volteron. And it is a project to get into industrial reality, into realization, our cold temperature electrolysis. There are other products, other metals that are produced through electrolysis, like copper or zinc. Why not steel until now? Okay, first of all, it's not straightforward. There are some big difficulties to overcome. But second, the economical situation, the economical context didn't allow this to succeed. It could not compete with blast furnace route. Blast furnace is a fantastic tool. It's very, very efficient reactor, and working with fossil coal, it has a really competitive cost. And all the steel world, all the steel industry is based on this concept. 70% of the steel nowadays is produced through the blast furnace route. And it's very difficult to find alternatives if you don't have the economical motivation. So we have opportunities in some location where we can enjoy really low cost of electricity, and at the same time we have motivation to decarbonize and leading the emergency of the global warming. Now we start to see how the legislation, the tax on CO2 emission, this is creating situations where these new technologies have an opportunity.
And that's the driver, is it? Because as you say, if the blast furnace is such an efficient process, what's the driver to experiment with an alternative, to invest this money in building an alternative, even if now lower cost renewable energy makes it a practical option?
I think that the real motivation, the final motivation, is that we cannot afford as a society to keep producing the things based on fossil fuel, based on fossil coal, because we are creating a problem. And today I think there is no discussion that we have an enormous issue with the global warming. And this is the final target, and this is what will motivate all the changes. But for this to happen, we need a transition, and we need a transition where we can survive as a company, where we can make money. R&D anticipated this. R&D knows this is coming. So what is our role? Our role is to look for the cheapest solutions that make it feasible. And we have to find technology and solution which is the most optimal that we can find today. And for this, we need to increase the TRL of some technology bricks, as we call them. We need to work not only on the technical side with R&D, but also on the logistics and even on the marketing of these solutions, because we need help. Producing carbon-free steel is more expensive, period. It's more expensive than doing nothing. And we need to find a balance, and we need the support of governments, but also of society, of our customers. We need to consolidate green premium for the green products to help the industry to decarbonize. And the governments, they need to help us. They need to put in place some mechanisms to favor this transition. But our role is to make sure that the technology choice is the best possible one.
I mean,
That's why
given that
R&D is working on these topics.
given that imperative, what's the end goal then? Is it an emissions-free steel process?
That's the end goal. You're fully right. And this is something that can be achieved. We all have the target of the 2050, and there will be several steps towards that. No, I dream of a plant, of a factory where we produce steel. We just get the raw materials in. We have electricity, of course, and we have an outlet for the products. And everything we send out is a product, it's a steel, is co-products, I like to call them, like slags that go for cement and other applications, for construction, materials that can be used in the battery domain, everything you can imagine. And we have to do that without contaminating, without polluting. No emissions to the air, no emissions to the water. And then it is a plant that generates well profit for our investors, and quality of life for our workers and for our neighbors. No? And it does without sending CO2 to the atmosphere. And it's possible. Technology will allow it. The technology brought the problem because we built a technology based on fossil carbon, but technology is the solution, period.
So listening to that, there's really three areas that you have to address then. There's the carbon footprint, there's the pollutants that you talked about there, and then there's the sort of the side products, what happens to them, the potentially waste products, but side products. We've talked a bit about reducing the carbon footprint using electrolysis. What about reducing the pollution? Because obviously you've got pollution at every stage of the process, from the sinter stage, you've got pollution elsewhere. How do you tackle that? Are there recent R&D projects that have looked at the pollution side of things?
Yes, I just want to highlight one topic. No, we are agnostic of the solution. We are exploring, as I mentioned, due to the large footprint. We need solutions for the blast furnace. We need solutions for the EAFs and maximization of scrap, and electrolysis is another path. No, but no matter the solution, we need to produce steel without polluting. We cannot work emitting dust and harmful material to the air, and neither to the water. And we know that this is a growing concern. More and more we see examples all across the world where the companies are in big trouble because they are unable to accomplish with the environmental regulation. The limits of emissions are going down and down. And our R&D was really pioneer in this vision. And back in 2008, we saw there was a huge need to work on environmental technology. And we started with some solutions, basically to minimize emissions in chimneys. We developed, adapted one technology taken from other sectors for steel, and more specifically for our sinter plant. Is the hybrid filter technology, which brings a strong reduction of capex, and at the same time it can reach the most stringent parameters in terms of emission, both of amount of dust and amount of NOx, SOx, and other pollutants.
This is a device that sits in the chimney where you're historically releasing dust and other contaminants.
Yeah, the first thing, we have chimneys in our plants. For example, our sinter plant is a major source of this dust, no? And we need to ensure that there is nothing going out from these chimneys, other than the CO2, the water, and clean gases, no? And this was, let's say, the first step. But now we have a bigger challenge, if you allow me to comment, is what we call diffuse emissions. Is all the dust which is not located in a duct, in a chimney, It can come from the yards. It can come from open process like coolers. It can come from the trucks moving in the plants and taking powder out of roads. And this is more difficult to address because it's not in a single pot. You don't know where it's coming from. And then R&D is working actively and has developed very clever systems to diagnose using a combination of cameras, AI algorithms to interpret the image of the camera and the events, LiDAR technology, laser scanning technologies to track dust particles in the air, sensor network, and all of that together in a digital platform is allowing us to diagnose what are the problems in a given plant.
Wow.
And with this diagnosis, we can steer the investments to solve the problems. And it makes a huge difference. The money you need to spend if you are blind and if you don't know where the source of the problem is huge. So again, we are helping the company both to be compliant, both to be a better neighbor for the people living around us, but also to save money, because our mission is to propose technology and solutions that make possible to solve the problem, minimizing the cost. No?
Tell me a bit more about the filtering then at the top of these chimneys, because there's obviously different technologies that go on there. How has that technology evolved, and how have you got to where you are today?
Okay, this is one of the first success in the environmental technology that we got in R&D, as I mentioned before. We didn't invent filtering. The standard of industry are two types of technologies. One is the electrofilter, and the other one is the box filter. No? Electrofilters are starting to be out of the current constraints, the limits that are imposed by the authorities. Back filters are at the limit. They are much better than electrostatic, but they still struggle to be able to control the emissions of some chemicals, of some gases, NOx, SOx. Then we identify in the past one technology which was not applied in steel. It was applied in cement industry, and it's what we call the hybrid filter. It's around 50% cheaper than the standard, than the conventional technology. We help indeed to disrupt this domain, this business, and to reduce the cost of installing these filters. And at the beginning they told us it's impossible, you will not do it, this technology cannot work for the composition of your fumes. But we started to ask ourselves why not, and for each not we found an answer and we found a solution, and finally it works.
Obviously there's a lot of water involved in the production process. Is that a focus as well as sort of the air pollution?
Well, yes, because it's not a secret that the world is facing a problem with water. The availability of water, drinkable water, is an issue. The water for agriculture is a precious resource, and we cannot spoil it. No? And when I imagine the ideal plant, it's a plant which does not need external water. It's a plant that can manage cooling process in a virtuous cycle, recycling water, not wasting it, not sending any contaminant to the rivers and to the lakes around us. So water is a big concern. Even more, scarcity of water can be a factor to stop industry. If you have a very high water consumption, there will be some geographies where you will have not enough water to operate.
So we've talked then about the CO2 side, we talked a bit about pollution. There's obviously the waste products, the side products of the production process as well, and historically you found markets for that. What's R&D doing in terms of circularity and trying to ensure that there's that completely, if you're going to reach that goal of a plant with no waste products, where's R&D going with that side of things?
Yes, I like to remind the people listening that the steel is already a product which is very circular. The degree of circularity of steel nowadays is pretty high. Everything you build in steel is likely to become scrap in the future, and to be reused for producing steel. And most of the production of what we call the steel byproducts, no, this is when you produce steel from iron ore. You need to separate the iron from the oxygen, but also from silica, from alumina, from a lot of materials coming with the iron ore. And then you produce a slag. And the separation starts in the BF, but it continues. There is some slag in the BOF, in the EAF, in the different steel kettles, no, the different process that we have. And these materials need to have an application, otherwise they will go to landfilling. And our target in the company and the mission of R&D is to make it possible, zero landfilling. Let's reuse everything we get out of the mineral, out of the raw material. We have today a situation based on the blast furnace steel production, and the slag of the blast furnace is mostly used for producing cement. There is a strong synergy, and we are helping the cement industry to decarbonize. But we are changing the blast furnace. Although we will keep some blast furnaces in operation because it's possible, and we will decarbonize some blast furnaces, we will also we are building a lot of EAFs. And then we are going to change the type of products that we get, because the nature of the EAF slag is not the same as the nature of the BF slag. It has not so good properties to go straight into cement. Also, the dust of the EAF is quite particular, and today we have some application for this dust, but this is based on the current mix of scrap and the current products. This is going to change, and then we have to find solutions also for this dust and for everything we produce as a co-product of steel making. And what R&D is doing? We are in contact with startups, we are in contact with OEMs, we have also developed our own ideas and we are testing them in the lab, and we need to find solutions to recycle materials, to cope with the closure of some sinter plants that will stop operating, because today we are using the sinter as a recycling unit. So what is the new technology? What is the TRL of this new technology? Today this is in TRL 4, 5. We are helping them to upscalate to TRL 6. And when we have some incoming projects, we will build some industrial pilots, and this will consolidate TRL 7. So basically we need to keep being an industry which recycles everything and which avoids landfilling. And by the way, in some plants, we are already there, very close. We need a little push, and especially we need solutions for the new production routes.
You mentioned the circularity of steel itself and sort of recycling scrap into the process. That obviously presents its own challenges. You know, scrap is of different qualities, have different contaminants. Is there any research going on to sort of improve the induction of scrap into the production process?
Yeah, that's a point which is critical and very urgent to solve. ArcelorMittal is very well positioned today in automotive, in tin plate. We are leaders in the markets, and we are leaders in industry, and we have an enormous history in producing very challenging products based on the BF road or the DRI road. It means virgin iron, not that much scrap, and not that much residuals and other things that come with the scrap.
Because you have to have such great control of the metallurgy to produce those steels, particular steels.
Of course, because the challenge is the following. We want to produce the top quality products from scrap. And this is not straightforward. And I would say, fortunately, it's not straightforward because this means that companies like ArcelorMittal will be leaders in getting the most difficult products based on scraps. No? And why we can be leaders? We can be leaders because we have a large footprint and a large history of producing with several production routes. We already have some EAF, which is producing some challenging products in Canada, in Mexico. But we have a big database of historical information. And we have teams inside R&D that are leaders, industrial leaders worldwide in the application of AI. And more specifically in mathematical optimization. when you put the knowledge of our metallurgical experts, you put the available data, and you put the AI expertise, really you start to learn how to use scraps. You how to learn how to master residuals. But it's not the only thing we can do. We also work in classifying scrap, in identifying composition of scrap, also avoiding some confusion or some issue, in the reception of scrap. Scrap is a very, very precious material, and we need to treat it as gold. We need to treat it as what it deserves. We are also developing technologies to clean scrap, to enhance its quality, and to enhance its classification. So when we have to produce challenging products in the EAF route, we will consider what type of scrap we need to add, in which percentage, with what amount of virgin iron, and this way, while doing that, we need to optimize cost. And all of that it can only be done with a scrap expert system in charge of handling scrap, with an EAF expert system to have automatic control of the EAF, and putting together all the knowledge of several disciplines, of several science, from the metallurgy to the AI, to the process of the different steps. And that's why we think we can lead industry in this, because of the history and because where we are and because of the strong R&D organization we have. We think that we can be leaders in adopting successful this technology faster and better than others.
So gaze into the future for me, Pedro. What does the steel plant of the future look like from the perspective of the success of all of those R&D projects, everything getting to your TRL 789? What does the future steel plant look like?
Well, really, what I cannot see is what are the technologies that will succeed. There are many options, and we are working in many of them, as I mentioned before. But what I imagine as a dream, is kind of is a plant which is enclosed in kind of a bubble, a dome, which not emitting any dust and any contaminants to the air. It's not affecting the water. It's not taking water. It's circular. It reuses water. We recycle the water, or we don't even need it. And we have an entry for the raw materials, and we have an exit for the products. And everything we take out of this bubble, giant dome, is products. Steel, products for construction, products to the battery industry, products for making chemicals, no waste, no impact in the surroundings, profitable, making money and creating wealth for our investors and for the people, for the workers and for the neighbors. And the people will not hate to live close to this plant. They will love to live close to it, because this way they can go to work in 5 minutes.
Brilliant. Thank you very much, Pedro.
We hope that you enjoyed our latest episode. Join us next time when we meet with Felipe Augusto Vasconcelos Guimarães, head of ArcelorMittal Mining's Research and Development team, to discuss the cutting-edge science being used by the team.